Welcome to our exploration of semantic networks and knowledge graphs. This is a first, short video to explain the fundamental structures that underpin the concept of graphs. But let's start by mentioning the most basic structure, which is a tree. A tree is a hierarchical structure with a root node at the top, branching out to child nodes below. Each node, except the root, has exactly one parent, creating a clear, top-down organization of data. Unlike trees, graphs are more flexible structures. In a graph, nodes, or vertices, can connect to multiple other nodes through edges, or arcs. There's no concept of a root node, and connections can form in any direction. This flexibility allows graphs to represent complex relationships that trees are unable to represent. Semantic networks, also known as knowledge graphs, were originally developed in the 1960s, and are seeing a resurgence today, particularly in managing and querying internet-derived knowledge. Graphs open up various search possibilities. We can perform intersection searches to find common elements, use inheritance to trace relationships, or employ advanced techniques like graph neural networks, GNNs, for more complex analysis. Another search method involves uploading the graph itself to a large language model, and have the model search for an answer, based on the information in the graph. Let us apply these concepts to a real-world scenario. For example, we can even think of this basic graph as a representation of a small company. The central node, labeled GM, represents the general manager. The other nodes, labeled with letters, represent employees or partners in the company. This structure allows us to visualize the company's organization at a glance. Now, let's populate our network with relationships. The edges between nodes represent various types of connections such as reporting structures, friendships, likes and dislikes, office proximity, and even marital relationships. Notice how this single graph can capture a wealth of information about the company's formal and informal structure. With our network in place, let's consider how we might extract information from it. Semantic networks excel at answering complex queries by traversing the relationships between nodes. For instance, we might want to find what two employees have in common, or understand the reasons behind certain company decisions. Let's try an intersection search. If we ask, what do Irene and Bob, represented by the nodes I and B, have in common? The system would look for paths that connect to both node B and node I, all from the same node. In this case, we can see that both node B and node I report to Edward, represented by node E. This type of search helps us find commonalities between entities in our network. Now, let's try a more complex query. Why did Henry, H, suddenly get a raise? This requires an inheritance search, but it also highlights an aspect of some semantic networks, the need for heuristic knowledge. Without additional information, we can't definitively answer this question based solely on the visible relationships. However, our network suggests that Charlie, C, who is friends with Henry, reports directly to the general manager, GM. This implies that Charlie may have played a role in Henry's raise. We need to clarify again that this inference relies on our understanding of how the world works, what we call heuristic knowledge. For instance, we assume that in a small company, salary increases typically require management approval, and that people tend to speak favorably about their friends to others. While obvious to us, this kind of common-sense reasoning needs to be explicitly represented in the semantic network for a computer to make similar inferences. In practice, this heuristic knowledge is often represented as additional semantic networks, interconnected with our main network. This allows our system to make more nuanced, context-aware inferences, mimicking human-like reasoning in navigating complex social and organizational structures. Some of these capabilities are readily available if we upload the graph to a language model, either as a picture, or in JSON format. Let's see how this works. Here's a prompt to one of the language models. It reads, "Attached, please find a knowledge graph showing the relationships between employees in a small company. We have heard that Henry recently got a raise. Do you see any clues in the graph to how this may have happened?" The language model's answer on the left speaks for itself, and proves that the language model has the associations necessary to understand the question, and also find a good explanation. The language model also explained its reasoning, and among others, why our own version regarding the question, "Why did Henry suddenly get a raise?" could make sense. That paragraph, highlighted in red, concludes with the words, "Since C likes H and is a friend of GM, this could have indirectly influenced the decision," if C spoke positively about Henry to the general manager. There are also other comments by this language model that are worth reading. All in all, impressive work by Anthropic's language model. To sum up this short introduction, knowledge graphs, traditionally known as semantic networks, offer a powerful way to represent and query complex information. By modeling relationships as graphs, we can uncover insights that might not be apparent in traditional, hierarchical data structures. In today's data-driven world, the ability to represent and query knowledge in this way is becoming increasingly valuable.